The ultimate beginning and the Planck epoch. The story we are about to tell is the grandest narrative of all, the true origin story of everything. It is the history of the universe, a tale of fire, fury, and fundamental physics. It begins not with a whisper, but with a colossal, all-encompassing event known as the Big Bang. This term, often visualized incorrectly as a conventional explosion in space, is more accurately described as the sudden, rapid, and ongoing expansion of space and time itself. To trace our cosmic lineage, we must journey back to the most extreme moment imaginable. Time zero. Imagine condensing the entire observable cosmos, every star, every galaxy, all the dark matter, all the energy, and the very fabric of space-time, into a single point of infinite density and infinite temperature. This is the singularity, the state from which our universe is hypothesized to have emerged. At this exact point, our everyday concepts of space and time simply cease to exist. Time itself is a measurable parameter within the universe. It did not predate the event. The physics governing this initial moment, beginning at time equals 0, and extending up to the tiniest measurable fraction of time, 10 to the power of minus 43 seconds, is called the Planck epoch. This fleeting interval, defined by the smallest meaningful units of time and space, represents the boundary of our current scientific knowledge. In this epoch, the universe's temperature was an astronomical value, estimated to be 100 million degrees Kelvin. Under such colossal energy densities, the fundamental laws of nature, which we observe as distinct today, are believed to have been unified into a single, perfectly symmetrical superforce. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were one. Physicists striving for a comprehensive theory of everything seek to describe this unified state. The challenge is that at this scale, the laws of the quantum world, governing the very small, and the laws of relativity, governing the very large, must be reconciled, a task that remains the greatest unsolved puzzle in modern cosmology. It is a realm of pure, undifferentiated energy, a condition so extreme it challenges the limits of human comprehension. As the universe began to expand and the temperature started its initial descent, the first crucial symmetry was broken, gravity separated from the superforce. This epochal event, marking the end of the Planck time, that minuscule 10 to the minus 43 seconds, set gravity on its independent path as the weakest, yet longest reaching, of the four forces. This sequential breaking of symmetries, like freezing water into ice, dictated the fundamental constants and laws that would shape all subsequent reality. It is worth pausing to reflect on the sheer immensity of this first act. The entirety of cosmic history, $13.8 billion years, is built upon the foundation of what occurred in this first, incomprehensibly brief moment. The very parameters that allow for nuclear fusion, stable orbits, and complex chemistry were fixed here. If the gravitational constant had been even slightly different, the universe either would have collapsed immediately or expanded too quickly for anything to ever coalesce. This fine-tuning speaks to the incredible fragility and precision of the initial conditions. Section 2, Cosmic Inflation, the great stretch immediately following the Planck epoch, when the universe was still less than a trillionth of a trillionth of a trillionth of a second old. It entered the Grand Unified Theory, GUT, epoch. At this stage, the strong, weak, and electromagnetic forces remained unified. While gravity acted independently, the universe was still incredibly hot. But the temperature drop triggered an event of truly cataclysmic proportion, one that rapidly cemented the large-scale structure of the cosmos. Cosmic inflation. This was not a gentle expansion. It was an explosive, exponential growth spurt of space-time itself. Driven by a hypothesized scalar field known as the inflaton field, the universe expanded at a rate far exceeding the speed of light. In a staggeringly brief interval, estimated to be around 100 billion billionths of a second, a region of space smaller than a single proton swelled to a size larger than the entire volume of space we can observe today. The scale of this expansion, estimated to be a factor of at least 1 followed by 26 zeros, is almost unimaginable. To put this into perspective, think of a patch of space no bigger than the smallest particle we can measure, and watch it instantaneously grow large enough to contain every star system, every galaxy, and every void in the current cosmos. Inflation serves as an indispensable addition to the Big Bang model, resolving several major cosmological puzzles. The first is the horizon problem. Without inflation, distant regions of the universe that appear to have the same temperature and density could never have been in thermal contact, which contradicts the near-perfect uniformity we observe in the cosmic microwave background. Inflation elegantly solves this by proposing that before this rapid stretch, these regions were close enough to reach thermal equilibrium. The subsequent expansion then stretched these uniform conditions across the entirety of the cosmos, preserving their shared history. Secondly, inflation addresses the flatness problem. Observationally, the geometry of the universe is incredibly close to flat, meaning the actual density is almost precisely equal to the critical density required for flat space. Any slight deviation from flatness in the early moments would have been exponentially magnified, leading to a universe that would have either quickly collapsed or expanded too rapidly for structures to form. Inflation acts like a cosmic iron, forcefully stretching the geometry so flat that any initial curvature becomes negligible, much like how a small spot on a rapidly inflating balloon appears nearly perfectly flat. The near-perfect flatness we measure today, $13.8 billion years later, is a powerful, lingering signature of this brief, violent inflationary event. Perhaps the most crucial role of inflation is its explanation for the origin of structure. Quantum mechanics dictates that even in the most uniform fields, there are tiny, inherent fluctuations, random, microscopic jitters in energy density. These are not flaws, they are fundamental characteristics of the quantum world. Inflation took these infinitesimal quantum fluctuations and instantaneously amplified and stretched them into macroscopic variations across the universe. These now stretched density differences, the slightly overdense and slightly underdense regions, are the seeds of structure. They are the initial blueprints for every galaxy, cluster, and supercluster that would eventually form through the slow pull of gravity. Inflation successfully transformed the microscopic randomness of quantum physics into the large-scale structure of the cosmos. providing a mechanism for the beautiful, lumpy, structured reality we see today. Section 3. Reheating, mass acquisition, and the particle zoo. When the inflation field decayed and inflation abruptly ceased, its colossal potential energy was converted into kinetic energy in a process called reheating. This flooded the universe with a superheated, dense plasma of elementary particles, primarily quarks, leptons, and their antimatter counterparts. This marks the beginning of the electroweak epoch, around a trillionth of a second after the Big Bang, with temperatures still exceeding 10,000 million degrees Kelvin. In this extremely energetic environment, matter and antimatter were constantly being created from pure energy and subsequently annihilating each other back into energy. Following the principle of $E=mc², energy equals mass times the speed of light squared. The particles themselves were largely massless, traveling at the speed of light, as the forces were still partially unified. Specifically, the electromagnetic force and the weak nuclear force were merged into a single electroweak force. A pivotal moment occurred as the universe cooled to a critical point around 1/trillionth of a second, the final force separation. The electroweak force split into the distinct electromagnetic force and the weak nuclear force. This separation is intrinsically linked to the function of the Higgs field, which permeates all of space. As the symmetry broke, the Higgs field activated, interacting with certain fundamental particles to give them mass. Suddenly, particles like electrons, which are crucial for forming atoms, slowed down and acquired mass, while photons remained massless, continuing to carry the electromagnetic force. This mechanism, confirmed by the discovery of the Higgs boson, is essential, as without it, no stable, massive particles could form, and the universe would remain a chaotic soup of light and massless components. The masses of all fundamental particles, from the electron to the top quark, were established in this fraction of a second. The universe then entered the quark epoch, which lasted until about 1/millionth of a second. It was still a quark-gluon plasma, where the constituents of protons and neutrons, the quarks, were too hot and energetic to be confined. They moved freely, held apart by the thermal pressure, swimming in a sea of gluons, the carriers of the strong nuclear force. The strong force, the glue that binds atomic nuclei, was in full effect, but its power was overcome by the sheer energy of the environment, forcing the quarks to remain independent. This period is often described as a cosmic soup or stew, intensely hot and dense, where the basic ingredients of matter had not yet combined into any recognizable form. Section 4. The matter-antimatter war and the birth of protons. The defining puzzle of the quark epoch is baryogenesis, the generation of the cosmic preponderance of matter over antimatter. If matter and antimatter were created in perfectly equal amounts during the reheating phase, the subsequent annihilation would have left the universe entirely composed of radiation, photons, with no remaining matter to form stars, planets, or life. The existence of our matter-dominated universe proves that a fundamental, minute asymmetry must have existed. The prevailing scientific theory suggests that this asymmetry is rooted in the subtle ways certain exotic particles and their antiparticle equivalents decay, violating a symmetry principle known as CP symmetry, charge parity symmetry. The outcome of this colossal matter-antimatter war was a stunning, yet tiny, statistical victory for matter. For every billion particle-antiparticle pairs that annihilated, approximately one extra matter particle survived. This minuscule cosmic residue is the genesis of all baryonic matter, the normal matter that makes up the stars, galaxies, and everything we can directly observe. It's a remarkable stroke of cosmic luck that this imbalance occurred. Had the scales tipped the other way, or remained perfectly balanced, we wouldn't be here to contemplate it. The very existence of everything is dependent on this ancient, fundamental flaw in symmetry. Around 1/1,000,000th of a second after the Big Bang, the temperature dropped to approximately 10,000 billion degrees Kelvin. This marked the point of quark confinement and the end of the quark epoch. The strong nuclear force, carried by the gluons, is unique in that its strength increases as the distance between quarks grows. At this critical temperature, the thermal energy could no longer overcome this force, and the quarks were permanently bound together. This sudden confinement led to the formation of hadrons, the composite particles. The most crucial of these were the protons, formed by two up quarks and one down quark, and the neutrons, formed by one up quark and two down quarks. The fundamental building blocks of the atomic nucleus were now fully assembled. The universe had successfully navigated the most extreme conditions and created the particles of stable matter. The cosmic recipe was coming together. Section 5. The Hadron Epoch and the 1-second milestone following the confinement. The universe entered the Hadron Epoch, lasting up to about 1 second. This period was characterized by intense interaction and decay among the newly formed hadrons. Protons and neutrons could still interconvert through interactions with neutrinos and other leptons. For instance, a proton plus an electron could convert into a neutron and a neutrino, and vice versa. This conversion process was driven by the weak nuclear force, acting as a dynamic balance between the two particle types. Crucially, neutrons are slightly more massive than protons, meaning they require more energy to exist and are intrinsically unstable when isolated. As the universe continued to expand and cool, the thermodynamic conditions began to favor the creation and stability of the lighter protons. This led to a gradual tipping of the scales away from equilibrium. The constant energy supply needed to sustain the heavier neutrons began to diminish. By the time the universe was approximately 1 second old, the continuous interconversion of protons and neutrons effectively ceased, a process called freeze-out. The weak nuclear force interactions slowed down dramatically due to the decreasing temperature and density. At this pivotal 1 second mark, the ratio of the two particles had been firmly established. There were now about 5 protons for every 1 neutron. This ratio is not merely an interesting detail. It is a cosmological prediction of immense importance. This precise 5-to-1 balance would directly determine the elemental abundance of the entire cosmos for billions of years to come, limiting the amount of helium that could ever be created. What does the universe look like at this point, at 1 second? It is a vast, rapidly expanding volume. many light years across, with an average temperature of approximately 10 billion degrees Kelvin. It is still incredibly dense, far denser than the center of our Sun today. It consists of a dense, extremely hot plasma soup of protons and neutrons. The newly stabilized matter particles, soon to be atomic nuclei. Free electrons, still unbound to the nuclei, traveling at high speeds. Photons, a thick, dense sea of high-energy light, constantly scattering off the free electrons, making the entire universe opaque. Neutrinos, an enormous number of these elusive particles, which had largely decoupled from the matter plasma, now free streaming across the cosmos and forming the invisible cosmic neutrino background. The universe has exited its infancy and entered its childhood, the lepton epoch. The energy is still too immense and the temperature too high for the strong nuclear force to bind protons and neutrons together into composite atomic nuclei. Any attempt at fusion would be instantly broken apart by the ferocious collisions with high-energy photons. The entire cosmos remains a glowing, opaque, and incredibly turbulent plasma. The first second was a cosmic blur of creation, expansion, and fundamental law-making. It established the scale of the universe, set the nature of its forces, and forged the fundamental particles of matter. It was a journey from a state of perfect, unified symmetry to a differentiated world defined by four distinct forces and a tiny, yet existence-defining, surplus of matter. The raw ingredients for all stars and life have been created. Now, the universe simply needs to cool down enough to start cooking. The stage is set for the formation of the first elements, which will occur in the next part of our journey.